In this video, I include some examples of problems involving application of differentiation to tangent and normal lines to curves. The examples were borrowed from a reputable fellow educator.
So imagine we have a simple graph in the xy plane. The tangent line to a function is a line that touches the graph of a curve at exactly one point without crossing the graph. And in order to find the equation of a tangent line, we just need the value of the derivative at that point of intersection and the coordinate point of the intersection. Then we can use the formula for the equation of a line in point-slope form to write the full equation of the tangent line. The normal line then will be the line that's perpendicular to the tangent line, but that also runs through the same point of intersection. This section will walk us through everything we need to know about both the tangent line to a curve and the normal line to a curve at that same point of intersection. Let's get started with an overview and a few examples of how to find the tangent line to a curve at a particular point. In this video, we're talking about how to find the equation of a tangent line to a particular function at a specific point. And in this particular problem, we have the function f of x is equal to 2x minus 1 raised to the fifth power times quantity x plus 1. And we've been asked to find the equation of the tangent line to this function at the point x equals 1. So remember that the tangent line is just the equation that intersects the graph at exactly one point, which is different than the secant line, which will intersect the graph at two or more points. The tangent line just skims across the function, intersecting it at exactly one point. Well, that one point that we're interested in is the point x equals 1. So at x equals 1, what is the equation of the tangent line? You can find the equation of the tangent line at any value for x as long as the function is defined and continuous there. So in this particular case, we're looking for the equation of the tangent line at x equals 1. So how are we going to do that? Well, here we have the formula in point-slope form for the equation of a line. And remember, in point-slope form here, we have three values that we need to pay attention to. First of all, the value of m, that's the slope of the line defined by this equation. And then we have the values x sub 1 and y sub 1. And these two together are a point on the line. So x sub 1 comma y sub 1 is a point on the line. Well, we've already been told that the point on the line we're interested in is the point at x equals 1. So we just need to find the corresponding value of y, which we can do by plugging x equals 1 into the original function. Because when we plug x equals 1 into the function, we're going to find the value of the function at that point, the y value at that point. So we're going to go ahead and say f of 1 because x is equal to 1. So f of 1 is going to be, and then we're just going to plug in 1. So here we'll get 2 times 1 minus 1 raised to the fifth power times 1 plus 1. And now we just need to solve for this value. So we'll have here 2 times 1 is 2, minus 1 is 1. 1 to the fifth power is just 1. And then 1 plus 1 is 2. So we have 1 times 2, or just 2, which means that we're interested in the point 1, 2, because x is 1 and y is 2. So this x sub 1, y sub 1 coordinate point is the point 1, 2. So we already have those values. The only value we need now is m. And m is just the derivative of the original function evaluated at the point that we found. So all we have to do is take the derivative, and we'll call the derivative f prime of x, because the original function is f of x, so the derivative is f prime. So f prime of x is going to be equal to, and now we need to take the derivative of this function. Well, we're going to need to use product rule in order to take the derivative, because we have the product here of two functions. The first one is this 2x minus 1 to the fifth. The second one is this quantity x plus 1. So we have two functions that are multiplied together. And so in order to use product rule tells us we take the derivative of the first function. So the derivative of 2x minus 1 quantity to the fifth power is going to be 5 times 2x minus 1 raised to the fourth. Then we have to multiply by 2. And the reason that this is the derivative of 2x minus 1 to the fifth is because we use chain rule. So to use chain rule, we bring the exponent, the 5, out in front. So we get the 5 out in front here. We're taking the derivative of the outside function, leaving this inside function completely untouched, and then we subtract 1 from the exponent. So 5 minus 1 gives us 4. But we just took the derivative of the outside function. We didn't deal with the inside function 2x minus 1 yet. So then chain rule tells us that we have to multiply by the derivative of the inside function. So this inside function is 2x minus 1. The derivative of 2x minus 1 is 2, so we have to multiply it by 2, and that's the derivative of what we've underlined here in purple. But then product rule tells us we're taking the derivative of this. Whatever we get, we multiply it by the other function without doing anything to it. So we're going to multiply by x plus 1. But then we have to add to that the opposite scenario. So here we took the derivative of the first function and we left the second function alone. Now we're going to leave the first function alone. So we're going to leave 2x minus 1 to the fifth power alone. And we're going to take the derivative of x plus 1. So the derivative of x plus 1 is 1. So we have to multiply this by 1. And now we just want to simplify. So here we're going to move this 2 to the front, and we're going to get 10 times 2x minus 1 to the fourth times quantity x plus 1. And then here, multiplying by 1 doesn't change the value, so we just have plus 2x minus 1 to the fifth. Now we could leave the equation like this, or if we wanted to, we could factor out a 2x minus 1 to the fourth. I'll go ahead and do that just to make it a little cleaner. So we're going to have 2x minus 1 raised to the fourth power multiplied by 10 times quantity x plus 1, which is what's left over when we pull the 2x minus 1 to the fourth power out of this first term. And then here we're just left with one factor of 2x minus 1. So we can just say 2x minus 1. Now we'll distribute the 10 across the x plus 1. And then we'll combine like terms here in this second set of parentheses. So 10x plus 2x gives us 12x, and 10 minus 1 is 9. So we'll get 12x plus 9, and we'll rewrite the derivative function as f prime of x is 2x minus 1 raised to the fourth power multiplied by 12x plus 9. Now to simplify further, we can factor a 3 out of the 12x plus 9. So we'll pull that 3 out in front, and we'll say 3 times 2x minus 1 raised to the fourth power times 4x plus 3. And now we've simplified the derivative function as much as possible. We didn't need to do that technically, but it just makes our final answer a little bit cleaner. So this is our derivative function. Now we just need to evaluate it at x equals 1. So instead of f prime of x, we're going to say f prime of 1, and we're going to plug x equals 1 into the right-hand side. So here we're going to have 3 times 2 times 1 minus 1 raised to the 4th power times 4 times 1 plus 3. And now we need to simplify to find the value of f prime of 1. So what we get here is 3. 2 times 1 is 2. 2 minus 1 is 1. 1 to the 4th power is still 1. So that's 1 for that first term. Here we have 4 times 1, which is 4. 4 plus 3 is 7. So we have 3 times 1 times 7, or just 21. So now this is the value m. So the derivative f prime evaluated at this particular point, x equals 1, is what we're going to use for the value of m. So now we have this value for m, and we have x sub 1 and y sub 1. So if we go ahead and box those so we know what we're doing here, we have m equals 21 going in here for m. We have x sub 1 as 1, and we have y sub 1 as 2. So we're going to plug in all 3 of those values using this formula here. So with this formula, we're going to say y minus y sub 1, or y minus y sub 1 is 2, equal to m, which we know is 21, multiplied by x minus x sub 1, or x minus 1. So x minus 1. Now we can leave our equation in this form, or we can simplify it by solving for y. So in order to solve for y, we'll first distribute the 21. So we'll get y minus 2 equals 21x minus 21. Then we'll add 2 to both sides to get y by itself, and we'll get y equals 21x minus 19. And this then is the equation of the tangent line to this original function here, f of x, at the point x equals 1. Now we want to talk about how to find the equation of a normal line to a curve at a particular point. Keep in mind that the normal line is just the line that is perpendicular to the tangent line. These are the steps that we're going to take to find the normal line. But before we walk through these, let's just get a visual picture of what the normal line looks like so that we can know what we're actually trying to find. So let's say, for instance, that we have this curve here, and we'll call this curve f of x, and it's just some generic cubic function. If we wanted to sketch in a tangent line, so let's say we have this tangent line here, this line is tangent to f of x at right about this point right here, it looks like. So if we come down here to the x-axis, let's just say that along the x-axis here, we're at -2. Then this is the tangent line to the function f of x at x equals -2. And so we can go ahead and say that this is the tangent line. We're already familiar with this tangent line idea, but the normal line is the line that is perpendicular to the tangent line at that same point. So it sits at a 90-degree angle. We'll go ahead and say that this down here is the normal line. And what we would want to indicate is that we have here a 90-degree angle because the normal line and the tangent line are always perpendicular to each other. That is the definition of the normal line, that it's perpendicular to the tangent line. So we have a right angle here, or a 90-degree angle. So this light blue line would be the tangent line to f of x at -2. And this dark blue line would be the normal line to f of x at -2. So if we want to find the normal line to a function at a particular point, like we've done here, what we do first is we find the slope of the tangent line, because we know that perpendicular lines have slopes that are negative reciprocals of one another, which means that if the slope of our tangent line is m, then the slope of our normal line is going to be negative 1 over m. This is the negative reciprocal because 1 over m is the reciprocal of m. And then when we multiply here by a negative sign, this is the negative reciprocal of m. So if the slope of the tangent line is m, the slope of the normal line is negative 1 over m. So we find the slope of the tangent line first, then we use that to build here the slope of the normal line, and then we take this slope of the normal line and this particular point here that we're interested in, and we plug those two things into the formula for the equation of a line, and that'll give us the equation of the normal line. So if we go back to this set of steps that we're going to work through, this set of steps will get us to the equation of the normal line every time. Let's say that we have a function, we'll call it f of x is equal to 6x squared plus 3. This is the function f of x we're going to start with. And let's say we want to find the equation of the normal line to this function when x is equal to 1. Well, the first thing we want to do is find the slope of the tangent line, which is m. So that's our first step here. We want to find m, and the slope of the tangent line m is equal to the derivative of the original function evaluated at this x value that we're interested in. So we take the derivative of our function and we say f prime of x is equal to the derivative of 6x squared plus 3 is just 12x. Once we have our derivative, we evaluate it at this value of x. So we say f prime of 1 is equal to 12 times 1, which is equal to 12. So that is the first step. This is the slope of the tangent line when x is equal to 1. Now to find the slope of the normal line, our second step here, we take the negative reciprocal of the slope of the tangent line. So step 2 is going to be that n, the slope of our normal line, is equal to negative 1 over m. Well, in our case, m is 12. So we get negative 1 over 12. This then is the slope of the normal line. Once we have this, we've finished step 2. We can move on to step 3. Step 3 here, this is just the formula for the equation of the line. You can see that we're using the slope here, n, for the normal line. And then we have to plug in for x sub 1 and y sub 1. Well, we already have x sub 1. This is the x value at the point that we're interested in. But we also need to have y sub 1. The way that we find that is by taking this value of x and plugging it into the original function. Because if we go back to our illustration here, pretend that this is our function f of x, we've already been told that this value of x here is 1, but we don't know the y value of this coordinate point. So we have to plug x equals 1 into the original function in order to get the y value at that coordinate point. So we have the full xy coordinate point. So we'll take x equals 1 and we'll plug it into the original function. So we'll say f of 1 is equal to 6 times 1 squared plus 3. That's equal to 6 plus 3, or 9. So now we can say that we have the coordinate point x sub 1 y sub 1 equal to 1, 9. This is the point along the curve that the normal line will be passing through. So now that we have that value, we can plug everything into this formula for the equation of the normal line. So we get y minus y1. Well, y1 is 9. So we get y minus 9 is equal to n, the slope of the normal line that we found, negative 1 over 12, multiplied by x minus x1, which we were given, that's equal to 1. Now we finished step 3. This could be the equation for the normal line. We could leave it this way, but sometimes it can be really nice to put it into slope-intercept form, which we do by solving for y. So if we solve for y, we'll add 9 to both sides, and we'll get y is equal to negative 1 over 12 multiplied by x minus 1 plus 9. And then it's nice just to simplify this right-hand side as much as we can. So we'll get negative 1 over 12 x. When we multiply negative 1/12 by negative 1, those negative signs will cancel, and we'll be left with positive 1 over 12. And then we have plus 9. Well, if we find a common denominator here with the 1/12, we'll multiply 9 by 12 over 12, and we'll get plus 108 over 12. And so our result then is y is equal to negative 1 over 12 x plus 109 over 12. So in this format, we've completed step 4. This is the equation of the normal line. In this format, we see that this line intersects the y-axis. It has a y-intercept of 109 over 12, which is just a hair above 9 along the y-axis. And then it has a slope of negative 1/12, which means that it'll move down 1 unit for every 12 units the line moves over to the right. So that's the equation of the normal line. Just remember, this is what the normal line looks like. It's perpendicular to the tangent line at that point of tangency. And we can always follow this set of steps here in order to find its equation.